Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process. Man can never be more intelligent than the Mother Nature. And in the last lecture, if you look at, we had discussed about mass conservation equation, right? And what we call continuity. And continuity is very important, isn't it? Not only in the fluid mechanics, but also in our culture. The continuity is being broken means you will lose the cultural heritage, so also the fluid mechanics, and all are continuum, right? We are working on the continuum mechanics, okay? So that is very important, and what we will be doing, and when the continuum is there, or it is continuity is there, and also that we need to look at momentum, how much momentum is there that makes the fluid to move, and so also the nation, isn't it? Momentum plays a very important role. And if you look at momentum, momentum comes from where? What are the causes of this momentum? Any idea? What are the causes? It's the forces, right, which will be acting, that makes it to have momentum, isn't it? Without force, can you have any momentum? Yes or no? So today we will be looking at momentum conservation equation that we will be deriving. And for that, what we will do? We will take as usual, that is a infinitesimally controlled volume, and as we had done in the last time, we are taking a two-dimensional situation. However, it can be extended for three-dimensional very easily, and we are taking Cartesian coordinate system. Let us consider a infinitesimally controlled volume. This is your delta x, delta y, and this is 0 delta y. And keep in mind that what do you mean by this infinitesimally small? The delta x and delta y, the distance, if you look at, if I say this is my distance, right, is too small, right, that is the meaning. Now we want to look at this control volume, right, this is my control volume, it is having, let us say, phase A and phase B, and this is your phase C and D, right. Just to have a feel, I am just putting this, it is not required as such. And now we will have to look at the momentum conservation. And what is that? That is basically rate of accumulation of momentum in the control volume, right, rate of accumulation or gain, I can say gain of momentum in CV is equal to rate of control volume minus, I can say, rate of momentum out of control volume, right, is plus, what are those things? Like sum of the forces acting on control volume, and this I can say is the equation 1, right. And when you talk about this, basically we will have to look at now the momentum conservation along the x direction and momentum conservation in the y direction, we will be looking at it. But let us now consider the momentum conservation along the x direction, right, along. So, if you look at what is this momentum in the x direction, that is entering into, this is rho V x and V x. What is V x? V x is the, let V x is the velocity along x direction, and V y is the velocity along y direction, right. And what is getting out from this face B, that is rho V x V x, right, and we will have to expand in the Taylor series, and assuming that delta x is too small and the higher order terms are not there. So, what we will write down? We will write down dx rho V x V x into delta x. So, when you look at this momentum flux which is entering into this, and you will have to apply into multiplied by the area. Rate of momentum along x direction, what it would be? Rho V x V x into delta y minus rho V x V x plus rho V x V x delta x into delta y, right. And this will cancel it out, right. This will be cancel it. If I just take this delta y into this, that will be cancel it out. What I will be getting is basically rho V x V x into delta x into delta y, right. This much I will be getting. Now, what we will have to look at now? We will have to look at along with the x direction, right, due to the fluid velocity V y, how much momentum flux is going in and out. So, that way if you look at, it is going this way. What is that? That is basically rho V y into V x. Similarly, here what is that going on? Rho V y V x plus by dou y rho V y V x into delta y. So, now it will be, if you look at, it is going through this delta x, right. So, therefore, the rate of momentum, this is basically y momentum, right, along x direction, right, in this control volume will be basically, I will not write down, is equal to rho V y V x into delta x minus rho V y V x y rho V y V x into delta y into delta x, right. So, this will cancel it out, right, this will be cancelling out. So, therefore, I will get minus V x V y into delta x delta y, right. So, and if you look at rate of accumulation of momentum, what it would be along the x direction, okay, along x direction. What we are doing now only along the x direction, right. That will be what? Dou by dou t rho v x into delta x into delta y. Of course, the volume 1 is perpendicular to this plane. So, therefore, that itself is a volume, okay, keep in mind that. So, now if you look at, we know in this term the left hand side and right hand side, both the terms we know, only we will have to look at the forces, some of the forces acting on the control volume along the x direction, right. So, if we will do that, now we need to look at what are the forces acting on the control volume. If you look at, we need to now evaluate it, some of the forces, right. What are the forces acting on this control volume? What are the forces? Pressure. I can of course, pressure will be acting, without that flow can take place, right. But I would like to look at in a little different way. That means, there will be some forces which will be acting on the surface. There will be forces which will be acting on the volume itself, right. So, therefore, I can divide these forces into two categories. One is which will be acting on the surface, right, and other will be acting on the volume. So, what are the forces which will be acting on the volume? Gravity, electromagnetic forces, right, and other things which we are not interested in except gravity. Why you will be interested in gravity? Okay. Gravity is not really very important, right. When the convective flow is taking place, gravity does not play a very important role, is not it? Yes or no? But however, we will be dealing with something diffusion flame, jet diffusion flame. We will be talking about droplet combustion, where gravity will be playing a role. There we are not looking at convection as a predominant, right. So, it is a natural convection which will be taking over. Therefore, we are keeping the gravity in our governing equation. We will be considering gravity, right, gravitational force, right. And the surface forces can be due to the shear stress, because it will be acting on the surface making the shear, right, and stress, force per unit area, that is the. So, therefore, it will be, we can say that due to these forces there will be created shear stress, right. You can say shear force also, and other is the normal, the two things which will be normal forces, right. Now, let us look at what are the things which we will be considering along the x directions, right. We will take again the control volume, right. Now, there will be force, which will we call it as a normal force, right, which will be acting, and that is we call normal stress in this control volume. This is a control volume, this is of course A, B, C, D, right, and this is delta x, delta y. I am just writing, I am not writing any other point now. And if you look at the force, the shear stress which is acting on here is sigma x x, right, and which will be acting here sigma x x plus sigma xx x into, of course, delta y. I can say this is into delta y, right. So, now the shear force which will be acting here, and similarly it will be acting in this direction, just opposite, because this force is opposite in direction, that will be y x plus y x by y delta y into delta x, because acting on this surface, this area, this is, this thing is basically delta x. Now, what is this tau? If you look at this tau y x, means this is acting on the surface y along the x direction. Okay. What is the tau y x? Is the shear stress, right, acting on y face, direction face, right, along x direction. Now, the net force acting on this fluid element, what it would be? Net forces acting on the what you call control volume in x direction would be equal to sigma x x plus x, I can put this way, right, into delta y minus sigma x x into delta y, right, plus tau y x y delta y into delta x minus tau y x into delta x. So, this will cancel it out, this will be cancelling out. So, I will get basically x x x plus y x y into delta x into delta y, right. And net body forces which will be acting on this, body force means gravitational force, what we are considering, okay, acting on control volume along x direction would be nothing but rho f x. F x is the body force along x direction. Basically, it will be body force can be anything, you need not to be gravity. If it is gravity, it will be g, okay, right, and rho into g, that is into delta x into delta y, right. And if I will substitute all these thing in equation 1, right, what it would be? It would be by substituting all the terms in equation 1 and what you call delta x tending to a 0 and delta y tending to a 0 conditions, right, we can have that basically what I will get? I will get rho v x by dt plus rho v x x plus rho v x v y dy is equal to x by dx plus y x divided by y plus rho f x. So, this is the expression what you will get, right. Let us say this is equation 2. Okay. Now, if you look at, we do not know really what is the normal stress, right. This I call it as a normal stress, and this of course I have already told you shear stress along the what you call x directions. And we can also do all these processes, all this by the similar way, by the analogous way, we can derive the momentum equation along the y direction. Keep in mind that this of course we call the momentum conservation equation along x direction, right. So, momentum equation along the y direction by using similar method we can derive momentum equation along y direction, right. That is V y this is basically momentum equation in the y direction, right. This is your momentum equation y direction. Now, keep in mind that these are what you call, if you look at rho v x, rho v y is, what are those things? Those are mass fluxes, where rho v x and rho v y are basically what you call the mass fluxes, isn't it? This is the mass flux, which is basically a vector quantity, right, because of the velocity is there, right, and mass fluxes along x and y direction respectively. And of course, the sigma, that is shear stress, and the sigma, that is basically the normal stress, and the tau is the shear stress which is acting on the surface of the control volume. And how we will take care? What we will do, because we will have to apply the Stokes viscosity law, right, and of course, this one can derive, which I am not deriving, but you can look at some standard books like any fluid mechanics book, you will get that by applying Stokes viscosity law, the surface stresses are given by tau x y is equal to tau y x mu y plus tau v y x and sigma x x is equal to mu 2 x by dx minus 2 by 3 v minus p. And keep in mind that this generally will be very small or 0, tending towards 0. So, therefore, you can say approximately equal to minus p. Similarly, sigma y y will be mu 2 dv y by dy minus 2 by 3 delta v minus p is equal to, basically this will be 0 for most of the cases and then approximately equal to the p. So, then when you substitute this equation, what you will get is basically final equation we can get x momentum equation dou rho v x by dou t plus rho v x plus rho v x b y minus dou p by dou x plus mu v x by x plus mu plus rho f x. Similarly, y momentum equation you can get as rho v y dt plus rho v x and v y dx plus y rho v y y minus dou p by dou y plus rho dx mu y by dx plus y mu dou v y by dou y and plus rho f y. So, this is the equation for Cartesian coordinate system, and however, we may use for the cylindrical systems, axisymmetric systems. What I am thinking that you please look at that and expressions, because or I can write it down for you, that is for an axisymmetric flow, we are only considering in the r and z directions, right, in cylindrical coordinate system. We can have, this is z momentum by dz rho vz or this will be vz vr is equal to minus dp by dz plus 1 by this is dou by dou z mu dvz by dz plus 1 by r mu dvz by dr and then rho gz. So, and the R momentum equation we can write down as and keep in mind that this I have considered as for the steady process, right. This is for the steady flow. Unsteady term I have not added in this. Okay. So, that is basically Vz Vr plus by R into R rho Vz Vr is equal to minus dP by dr plus rho dz mu Vr by z plus 1 by R d by dr R mu dVr by dr plus rho g r, right. Direction just to say, but gravitational force if you are considering, right, that will be rather I would like to write it down here rho f z, this is general body force, okay, rho f r, okay. These are the body forces what we are considering, and if it is gravitational it will be g, okay. So, with this we will stop over. Keep in mind that we will be revisiting these things later on whenever we are looking at the flame kind of thing for analysis. Thank you very much.